thanks very much for coming along to this Work Package 7 Science Hour, which is going to be about the impact of Gulf Stream precipitation on North Atlantic jet variability. I have included a very nice video here, animation made by Thomas Rocco from well, not quite what we're going to achieve in EERIE, but something, what we would like to have. And so somehow the question is, what might we expect if we actually were able to simulate the Gulf Stream, anything resembling this kind of fashion? Oh, okay. So just to show the usual funding slide from the EU and the UKRI, we're all very grateful for that. Before I start, I need to advertise the next Science Hour already, which is going to be on the 2nd of May at the same time, so 4 p.m. European time. And it's going to be Rain, actually, who's going to be talking about intermodal differences in the representation of AMOC forcing on the NAO. And the location is the same. It's this same. Sorry, I wrote Zoom room, but it should be WebEx. But it's this same place. So put that in your calendars.
Okay, thanks for announcing it.
Yes, of course, Rain. Okay, so the Gulf Stream, right? So the Gulf Stream is a really obvious thing to look at in the context of EERIE. Of course, it sits somehow squarely in the center, at the intersection of all these things that or the key things we're interested in, model resolution, air-sea interactions, and, well, if you're in Work Package 7, certainly you care a lot about North Atlantic jet variability. And then, the Gulf Stream is, of course, very natural to think about in that context. So that's basically the general motivation. Just some preliminary points, which I don't want to have to repeat again and again. So I'm going to state them now and then never again, probably. I'm always going to be talking about the winter season, December, January, February, DJF. The time period I'm going to be focusing on is the kind of modern satellite period, 1979 to 2015. Stopping at 2015 because of the simulations stopping there. When I'm talking about the jet, it's always measured at 850 hectopascals, and when I'm talking about blocking, that's measured at 500 hectopascals. And so there was this phrase pre-EERIE data in the title, right? And what that means in practice is just as much of CMIP5, CMIP6, and high-res MIP data that I could get my hands on. So roughly speaking, the results are going to be based on 135 individual coupled climate model simulations spanning these three protocols. And finally, just to mention, of course, there's absolutely enormous amount of things you could say about the Gulf Stream and how it relates to North Atlantic climate variability. And I'm only going to focus on quite a specific point, and apologies if that isn't your kind of favorite aspect of this story. One could talk for hours. Okay, so just to get the context, if we think about how models are performing at the moment, then the rough picture is that modulo a lot of internal variability, the model jets, and again, just emphasizing, I'm talking about the North Atlantic jet. The jets are too zonal and too fast. They underestimate European blocking, and they generally don't move northwards enough. So the plot here is just showing CMIP6 models, probability distributions of the daily jet latitude and the daily jet speed on the right. So the thick line is error 5 in these plots. So the jet speed, you can see, it's too fast, and that's tightly linked to this overly big peak in the center of the jet latitude distribution. So just to remind you, or just point out, the jet latitude is just, there's just some standard way of trying to estimate at what latitude the eddy-driven jet is sitting on a given day. And if you estimate that on all days in the winter season, then you can make a PDF like this. And Tim Willings found that this is trimodal, which is why it looks trimodal here too. So you can see there's loads of variability between models, but these are kind of some general features, a general way of describing the kinds of biases we see. Here's just to focus, because the previous plot doesn't really show European blocking very sort of clearly. Here's a nice figure from a paper by Davini and Andrea, where looking at European block, or just generally blocking biases in CMIP6, and you can see there's this big blue blob around the UK and Western Europe, and that's this underestimation of European blocking that I'm talking about. So this is, of course, a well-known and long-standing bias in climate models. So before I get on to talk about kind of more about the Gulf Stream and how the Gulf Stream might relate to this stuff, I thought it might be helpful, for people who aren't used to thinking about this stuff and jet variability, a lot, then just to remind you of a kind of simple conceptual way of thinking about jet variability and therefore also things like blocking, which we can then use as a sort of basis for understanding the role of the Gulf Stream. And the conceptual model I wanted to talk about is this predator-prey model from Ambaum and Novak in their 2014 paper. It's a very neat nonlinear oscillator model, which basically describes the life cycle of the jet or storm track in terms of these three phases. So to start with, you've got some kind of initial neutral state where the baroclinicity is low or close to zero. And then at some point, you get some instability arising and you have a growth state where the baroclinicity starts growing. And then you get a release phase where the baroclinicity exceeds a certain threshold, and then the atmosphere responds by then having a period of enhanced eddy and storm track activity by which these instabilities are moved polewards and allowed to dissipate. And then of course, the baroclinicity drops back to kind of neutral conditions again, and then you're back at the start. And what this means, and when you can construct an explicit nonlinear oscillator model of this, where you get these kind of this sort of cyclic behavior of the jet, where the jet kind of you get these northward shifts of the jet. So actually, I'll emphasize that in the next figure straight away, that in this release period, right, where they're associated typically with these northward shifts and also things like European blocking. So if you've never done it before, it's a fun thing to open up, load in some zonal winds at 850 daily values using NC view, and you can just look at the animation for a while, and you can kind of see this cyclic behavior happening where the jet kind of starts out down south and then it shifts up north and then cycles back around again, essentially. So you can kind of see that a little bit in this animation, perhaps. Okay, so with that in mind, we can think about, well, what effect does the Gulf Stream have, or might the Gulf Stream have, on things like jet variability and blocking? Well, there are two obvious things. It affects the growth phase in this predator-prey model, because the sharp SST gradient of the Gulf Stream is itself a source of baroclinicity. And I'm just showing here, just for context, right, the figures showing the zonal wind mean of Air 5 at 850, so that's the sort of typical position of the jet, you can see, and then the line contours are showing the SSTs again in Air 5, so you can see the Gulf Stream popping out from the continent. So yeah, so the gradient, the sharp gradient affects the growth phase, but the Gulf Stream itself also affects the release phase, because the warm waters of the Gulf Stream allow for a lot of heat fluxes and precipitation, which can generally produce bigger and stronger cyclones that can then move further poleward before dissipating. there's a kind of question mark I've put here around like mesoscale eddies. Of course, that's somehow what ERIE is going to look at. I think currently the role is slightly unclear, but I'll come back to the potential, I'll come back to that point at the end of the talk. Okay, so there have been experiments and work already done looking at both of these potential ways that the Gulf Stream can affect the variability. So I'm just going to highlight a couple here. So there are two papers by Chris O'Reilly et al., where they took a couple climate model and basically gave it first realistic looking SSTs, and secondly, they gave it a kind of smoothed SST. So you can see in the top figure, that's the kind of realistic SSTs, and then in the bottom one, they replaced it with a kind of smoothed version to get rid of these sharp SST gradients. And what they found then is that the effect that had is it reduced the amount of European blocking and the amount of northern jet days. So by which I just mean, days where the jet is very northward. So it's this northernmost peak in the trimodal jet latitude distribution in particular. In more recent years, though, a lot of people have been studying more closely the role of diabatic processes around the Gulf Stream. So this is this stuff I was talking about with the release phase of the jet variability. So there are many case studies arguing that these diabatic processes around the Gulf Stream are really important. And this is a particularly nice paper, I think, by a recent paper by Marta Wente et al. So the figure is taken from that paper here, and they're basically showing they explicitly calculate trajectories of air parcels that interact with a particularly strong blocking, which happened in February 2019. And what you can see, what this plot is showing is that these parcels basically all originate around the Gulf Stream, and it's not just that, that's kind of obvious, but the fact that when they are there, they pick up a huge amount of moisture, which then is transported northwards. And then they argue that so they argue that the source of moisture that the Gulf Stream gives was sort of crucial for the development of this block. I also want to highlight a very recent preprint by Matthews et al., including Chris Roberts as a co-author, where they also do some idealized experiments using the IFS, which corroborates this picture. So there's another very nice paper from last year which starts to touch upon the role of resolution here, atmospheric resolution. So a paper by Sebastian Schem last year did this these idealized studies using a regionally refined grid. So this figure is kind of sort of highlighting where the grid refinement is happening in these rectangular boxes. So outside the rectangle, there's a kind of coarse resolution, and then inside the big rectangle, the resolution increases, and then it increases again in the square around the Gulf Stream. So it's like very high resolution there, about 14 kilometers, if I remember correctly, in the actual Gulf Stream region itself. And what Schem finds and what this plot is demonstrating is that when you do that, you get more cyclones moving further north. So that's what the kind of the fact that you have this red, the red values on this figure being northwards here. It's telling you that you're getting more northward traveling cyclones when you increase the resolution here. And so Schem then argues that these biases we see about blocking and overly zonal jets are due to poorly resolved diabatic processes, and that the atmospheric resolution will help alleviate that. So what do we actually see in terms of improvements for resolution? Well, again, Davini and Andrea looked at this in CMIP 3, CMIP 5, CMIP 6, and they found indeed that basically blocking frequency, but the bias goes down as atmospheric resolution it goes up. So this is both for European blocking and also for things like northern jet latitude days. And then since Devine and Andrea, then there have been a few papers that do similar things and find similar results in other contexts. So the question is, it's an obvious question, and why do we get these improvements with resolution? So there are kind of three, or at least I'm aware of three kind of explicit hypotheses in the literature. One is reduced SST biases in the North Atlantic. So this is kind of looked at by Devine and Andrea, and I'd say they found sort of somewhat ambiguous evidence that this was a strong driver of these improved of the reduction in the blocking biases. The second one is that changes to SST gradient, that basically the argument, and this is an argument put forth by Athanasiadis and also by Michel et al., where they argue that the increased ocean resolution causes the Gulf Stream to separate more realistically, and that changes the SST gradients downstream in the North Atlantic. And those changes to the SST gradients cause these improved jet variability. And a crucial point there is in that argument is in both of those papers is a comparison between coupled and AMIT models, where by AMIT model I just mean model with forced SSTs. So I'm going to talk more about that comparison later on. Yes, but then the third one is the third kind of hypothesis out there is the one I just mentioned from Shem et al. Not Shem et al, just Shem, where the hypothesis is that improved precipitation variability in the Gulf Stream region is somehow the key thing which is doing this. And it's not just Shem, there have been other case studies making implicitly suggesting the same thing. So that brings me to today's goal, which is I wanted to basically a lot of the papers that have looked at these kind of effects of kind of diabatic processes in the Gulf Stream have focused on either looking at observational data or it's been case studies with a single model, and it's natural to explore these things using many models. And in particular exploring then the role of Gulf Stream precipitation and how it links with model resolution. I also want to, like I already alluded to, I want to talk about the potential pitfalls of comparing coupled and AMIT models, which is something which we're going to have to deal with in ERIE as well. And then I'll end with some speculation on, what we might see, what we might hope to see in mesoscale resolving simulations. Okay, so let's quickly go over the metrics just for completeness. So blocking, we're computing blocking following Athanasiadis et al. It's just a very standard way, reversal of a Z500 gradient. And there's no, it's just computed, on a daily basis. There's no kind of temporal threshold, like it doesn't have to last for a certain amount of days. It's just straightforward. And then when we define the Gulf Stream region, then again, I just follow what Shen did in his paper, and I'll show you what that looks like in just a moment. So the European block, and the region I'm going to call European blocking is this highlighted in this box here, and this figure is taken from Athanasiadis et al., where they basically, this is where you have this big, it's not just where we have a particularly big bias against observations like we saw earlier, but it's also where Athanasiadis et al. Find this particularly big improvement with resolution, which is what this figure is showing, the bias reduction as you increase resolution. Okay, so I say precipitation variability. Before I'll tell you what it is, but I better address the warning here in big black letters, which is that it's really essential. I mean, I'm sure most of you know this, but I have seen examples that don't do this, and it's really crucial to not use ERA 5 as precipitation, because it's a model precipitation, so it has this drizzle problem, just like all the models do, and the variability is rubbish. and you need to use something like satellite or whatever, and we used TRIM. Okay, so with that out of the way, so how are we measuring precipitation variability? So sorry, there's a typo here, but basically it's just monthly. Yeah, so sorry, it should say max monthly precip, not monthly precip. Maximum, it's the maximum monthly precipitation obtained in the Gulf Stream region across any of the December, January, February months. You could also have used the standard deviation of daily precipitation instead, and basically got equivalent results. And probably that's the better thing to do, but anyway, I haven't updated all my figures yet, so we're just going to stick with this measure of variability. Probably any metric which just measures something beyond the mean is good, will do the job. And the reason for that is because, first of all, Sham showed in his paper that the main impact of this increased resolution comes from the biggest cyclones. So there's not much change to the kind of mean cyclone, but like the sort of particularly big ones where this extra resolution creates gives the benefit. So you want to kind of measure something about the extremes of the distribution of the variability somehow. And the second key point is just that the mean precipitation isn't that bad in models because you know, it's very tightly constrained by just the energy balance of the atmosphere, which is models often tuned for, right? So the mean precipitation doesn't necessarily look that bad, but if you look at anything to do with variability or extremes, of course, there's massive biases. So you might hope to get a more accurate picture in that context. Okay, so let's get into some actual results. So here I'm showing Gulf Stream precipitation. So here on the bottom left is the multi-model mean. Again, that's just across all these models, which span a bunch of different resolutions and generations. And then in the middle, we've got the TRIM product, and then on the right, you can see the biases against it, and you can see there's this very big bias. It's on the order of about 50%, almost 50% bias compared to observations, smack bang in the Gulf Stream region, and the black box is indicating what I mean by the Gulf Stream region as well. You can also see, so the contour lines are the SSTs, and you can see this typical expected bias where the Gulf Stream doesn't separate properly in the models. It hugs the continent essentially in the models while it separates off the coastline much earlier in the real world. This is just showing that again, like just for completeness, showing the SST biases. And we see these kind of, so you can see that on the left, it's the mean average, multimodal mean SST, and you see this kind of very zonal Gulf Stream sticking out. So in particular, the models don't do this kind of turning at the northwest corner either. It's not just the kind of Gulf Stream separation, but they also don't do this turning. And you can see the bias on the right, and of course, there's, as you'd expect, there's a clear bias of the SST gradient, and then of course the associated or somehow related cold bias in the North Atlantic. Okay, how am I doing for time? Okay, so here I'm just kind of showing, so these are correlation plots. Essentially, the way to interpret these plots is essentially, so I'm kind of I'm correlating against the multimodal spread. So it means that, say on the figure on the right, the fact that there's red, positive correlations there, it means that models that have more Gulf Stream variability, precipitation variability, have a more positive climatological Z500 value at that point. And similarly on the left, it's showing how the jet kind of co-varies with the precipitation variability in models. So you can see the kind of straight away now that models with more precipitation variability have a northward shifted jet, and they have this big positive Z500 anomaly right over the European kind of blocking region, which is this black box. So that's kind of promising already. And then, of course, you can just actually compute some explicit metrics. So bottom left, it's now showing the actual, scatter plots of this Gulf Stream precipitation maxima against on northern jet days, the number of northern jet days, and on the right, it's against the frequency of European blocking. And the red star is observations. And I've estimated some internal variability by bootstrapping observations. And what's nice here is that the correlations are quite high. In particular, and somewhat to my surprise, there's a particularly strong signal for blocking. So the correlation there is about 0.7. So it means that approximately 50% of the intermodal spread is associated with these differences in the Gulf Stream precipitation in models. What about resolution then? Well, as you'd expect, as you increase the atmospheric resolution, precipitation is better resolved and the variability improves. So top plot is showing resolution. So atmospheric resolution as estimated by the kind of the grid spacing in kilometers at the equator. So as you move from right to left, you're moving from very coarse resolution to very high resolution. So on the top, you're seeing that precipitation variability is going up with resolution. And interestingly, there's some kind of, it looks like somehow some details about the convection parameterizations are maybe leading to some interesting, almost bimodal-esque differences between some of these models. But yeah, don't want to make a strong claim about what's going on. But what also seems clear is that it's perhaps not a linear growth. I've just fitted quadratic here. This not claiming that's what theoretically is going on, but if you do fit it quadratic, then and then see how well a job that does, the correlations you'll get jump up to about 0.75. So anyways, that's just saying that atmospheric resolution is a good predictor of precipitation variability, as you'd expect. And of course, there have been experiments noting that before, including this paper by Scher et al., which Rain was also involved in, where they did this kind of thing for ECF and found the same kind of thing. Okay, and the bottom one is basically reproducing the result of Devinian and Rea, which is that the blocking frequency goes up with resolution as well. Okay, so the summary so far is that Gulf Stream precipitation variability does indeed look like it is tightly linked to European blocking frequency in this very large multimodal ensemble. Excuse me. And that this precipitation variability goes up with resolution. And then you can also do some kind of statistical test for mediation. So the obvious pathway here that you would hypothesize is that the resolution is going up, that leads to better precipitation variability, and that causes more realistic blocking frequencies. And you can do some statistical test to test this, pathway, to test whether precipitation is a mediating kind of variable for the effective resolution. And you do, those tests will tell you that support that hypothesis, in the sense that you get some p-values less than 5% if you do that. I'm going to jump over there. I don't think I'm going to mention all these points. I just want to flag maybe at this point that there are lots of things that I haven't discussed that could play a role and could obfuscate the results, like indirect effects from other biases or compensating biases, model tuning, coupling, blah, blah, blah. These multimodal plots the multimodal plots tell a simple story in the way I've showed them, but there's no doubt that there's it's probably masking a certain amount of complexity. Okay, but in the interest of time, I'm just going to get on to the next bit, which is this stuff about atmospheric versus oceanic resolution. So as I already mentioned, this is a kind of argument that comes from papers by Athanasiadis et al. And also from Michel et al. Sorry, it should say Athanasiadis et al. 2022, not 2019. Anyway, so what they observe is that the link between jet variability and blocking and resolution is a lot smaller in the AMIT models than in the coupled models. And they interpret this as evidence for the role of oceanic resolution as opposed to atmospheric resolution. In other words, they argue that, that suggests that the improvements are coming because of the ocean resolution. Of course, in all of these plots, I was showing you kind of atmospheric resolution, like I was showing you like blocking as a function of atmospheric resolution. But I mean, atmospheric resolution and oceanic resolution are tightly correlated in all those models, right? When models increase for atmospheric resolution, they almost always increase for oceanic resolution as well. So, so you can't kind of tell from those plots a priori which is doing the heavy lifting. But this is the argument that these papers give. However, it's very important to realize that AMIT models are really very different to coupled models because they experience this problem of excess thermal damping, which means that their temperature and precipitation variability is considerably smaller than corresponding coupled models. So this was already highlighted by a sort of classic paper by Battisti and Basugli in 1998. And I'm showing, this plot is showing you kind of, the top figure is showing you a good example of that. So here it's the Primavera, so the high-res MIP models. So it's the standard deviation of daily precipitation here. On the right, so the black one is the kind of standard deviations you get in coupled models, and in the red it's from the AMIT, from the corresponding AMIT models, right? So there's a one-to-one kind of match here. And you can see that like they're completely separated, these distributions. So even the highest resolution AMIT model has significantly less precipitation and temperature variability compared to the lowest resolution coupled model. And the bottom plot, I won't talk about, it's basically, it's reproducing the kind of argument that Battisti and Basugli give, which is that it's because of bad ASE coupling that this happens. So an ASE coupling you could measure in terms of lag correlations between 2-meter temperature and SSTs, and what that plot is just showing you one example of how a particular AMIT model is very different from a particular coupled model in terms of this ASE coupling. And the upshot here is that these smaller signals that we see in AMIT models are therefore expected a priori, even without any change to the ocean resolution. And therefore, you can't really easily conclude that, you can't really easily conclude from the difference in AMIT versus coupled that it's the ocean which is doing the work. And this, I should emphasize, this poses quite a big challenge for EERIE as well. Of course, we have our sensitivity experiments planned, AMIT style models, but we have to, I'm not saying this is insurmountable. I mean, there might be ways of kind of accounting for this thermal damping effect, but it's something we have to be really careful about when interpreting results. Okay, and following on from that, I mean, there's also just generally, my impression from the literature is that the current evidence for improvements due to a better actual Gulf Stream seem a bit weak. So I mean, I've only been talking about Gulf Stream precipitation over the Gulf Stream region. I haven't been really talking about the Gulf Stream itself. And I mean, this paper by Tarsali et al. I've quoted here. They basically suggest that only the 12th degree ocean model correctly simulates correctly simulates the Gulf Stream separation. So basically no other model actually in their opinion, really changes the Gulf Stream separation bias. Yeah, I think I'm going to ignore the scatter plot here. Yeah. So that takes me on to my speculation, where the caveat is that I'm not an oceanographer, so you know, I hope more knowledgeable people might weigh in afterwards if you have an opinion. But of course, one thing we might hope to gain from mesoscale is of course then a consistent Gulf Stream separation in all the models. There's also this thing about the northwest corner, so you know this turning of the Gulf Stream, which you see in Area 5 in the middle, which is as far as I understand, an effect of bathymetry. So it's very deep. The ocean floor is very deep around that corner, around that corner, and I have no idea actually if that is expected. If you know, the frontier models are expected to produce that turn, and if they do, what will that achieve? And if they don't, what does that mean? And of course, we will hope that North Atlantic SST biases are going to be reduced as well. So yeah, I realize I'm not including a speculation on how these changes might manifest in terms of the jet variability. Because I think that's very unclear. We just don't have enough models doing these things to really have a good idea at this point. But there's one intriguing bit of evidence, or another intriguing line of evidence, which I wanted to highlight, which is again from a very recent paper by Yang et al., where the title of the paper says it all essentially. Observations reveal intense air-sea exchanges over sub-mesoscale ocean front. And this is, I think, the standout figure, or like most clear figure. It's showing a heat flux gradient as a function of SST gradient. So it's got some different, models and some reanalysis products. Those are the things in the bottom left corner here, and then you've got their more realistic observations. It's the black star way up there in the top right corner. So, there's a massive gulf here between what models might be doing and what we might expect to see if we actually resolve mesoscale. So what this is telling us that, of course, a lot of improvement to things like precipitation in the Gulf Stream you'd expect to come from atmospheric resolution alone, but papers like this suggest that there might really be a dramatic impact, a kind of step change, really, once you resolve the mesoscale. And that's kind of pleasing because if you extrapolate the current trends, you look at, I've shown you these figures, right, of how blocking frequency and the northern jet occurrences change as a function of resolution. If you extrapolate those to what you'd expect at a 10-kilometer resolution, you get this figure. So the red observations of black is the extrapolated or the kind of projected multimodal distribution. And you can see that based on current extrapolation, you're still going to underestimate these things. So I think a really exciting it's sort of a question here is whether these kind of intense air-sea exchanges highlighted by papers like Yang et al. Might mean that we actually we do better than extrapolation, that we really go up a kind of more step change up towards where we really want to be. And that's basically taken me to the end, just showing the funding slide one more time, and then I'll put it on my conclusion slide. So yeah, just to conclude, therefore, as consistently with all these case studies and observational studies, it really seems like diabatic processes in the Gulf Stream are very clearly linked to European blocking frequency in climate models. And a plausible pathway a plausible hypothesis explaining what we've seen in resolution so far is that higher resolution gives you better precipitation variability, and that reduces the blocking biases. So this seems like a nice explanation. There's this ongoing challenge about attributing atmospheric versus oceanic resolution, which, I don't know if there's ever going to be an easy answer to that. And then, these tantalizing suggestions about possible step changes in, when we resolve the meso scale. Okay, that's about 45 minutes. So, okay, I'll stop there. Thank you very much for listening. And of course, I'm happy to take questions or comments if there are any.
Okay, perhaps then, given that my video is on, thank you very much, Kristian. That was very interesting, and I think timely to see this overview, also a bit sort of a review of what's our current understanding. Perhaps two sort of initial questions. I mean, number one is, we compare the models with observations, and sort of, I mean, the atmospheric circulation in the North Atlantic, has been since the late 1970s, I think, a bit unusual. Okay, I mean, it has been very persistent, and I'm wondering sometimes to what degree, we are trying with models to recover something that maybe have to do with sort of something unusual in the atmosphere. And if you don't have this in your initial condition, then sort of you inevitably have to underestimate blocking. So I'm wondering sometimes to what degree we have an issue with blocking, which also brings me to the second part. Sort of how bad is it? If you would sort of now pick the best coupled models, sort of what's your take? How bad is it, is the underestimation of Euro-Atlantic blocking? Perhaps if you could comment on the two.
Yeah, excellent questions. I'll start with the second one. I mean, I think it's a good, I think the biases we still have in the jet and blocking are perhaps overemphasized a little bit nowadays. I mean, there has really been a lot of improvement from, all the way back from CMIP 3. And so the biases are not that huge anymore. I think for European block, I guess my impression is that for things like jet latitude variability, I'd say the CMIP 6 models are doing a pretty good job actually now. I think for Europe, things like European blocking, there still does seem to be a systematic issue which we'd really like to fix, but it's not something not nearly as bad as it has been in the past. I should emphasize perhaps also that when it comes to how good the models are, I mean, I was only looking at the frequency of occurrence and didn't think about things like the persistence or other kind of temporal characteristics of these blocks, which is another area where you can sometimes have more systematic biases in models. So I don't have a strong sense of how bad the biases are there. Coming back to the first question, as I understand it, I mean, it's a question about decadal variability, right? I mean, is there some decadal variability in the real world, which meant that blocking happened to be just a little more intense or more frequent? Obviously, that wouldn't necessarily be represented in models. I think that's a great question. And there is decadal variability in the jet, and some aspects of the jet anyway, not all aspects of the jet as far as we can tell. So things like the speed of the jet very clearly exhibits big decadal variability, but other aspects don't seem to show so much. I don't have a good sense of how well understood decadal variability of blocking is, like if it's and of course you always have these issues there. If you go back in time and the measurements drop as you go back in time, and it can get a bit tricky to place a really strong quantitative question. So I mean, basically I can't answer your question, Thomas, but I think it is a really important caveat to keep in mind. Yeah, absolutely.
I remember from my PhD thesis, there was this plot by Jim Harrell where he looked at the autocorrelation of the North Atlantic Oscillation Index, and he's shown that basically it was zero, for the first, I don't know, 3/4 of the 20th century, and then it started to redden. So the autocorrelation set in, suggesting that, I mean, back then it was time series until the turn of the century, so 2000 or so, perhaps a bit earlier, but that, certainly low frequency variability in the atmospheric circulation set in, okay, which is unusual in a way. And somehow this, somehow when in the early 2000s, when sort of research moved a bit away from the NAO, I don't think it has been picked up, but I still have in front of my eye this increase in autocorrelation of the NAO index, sort of around the late 1970s. And yeah, anyway, that's something to revisit.
Yeah, thanks. I'll take a look. I'll take a look into that. Thanks for the tip. Anne, I think you have your hand up.
Yes. Do you hear me?
Yep. I hear you.
Okay. Yeah. So thanks for this presentation. So I'm not expert in atmospheric physics, so it's a question of, I mean, I have no idea whether it's something very well known or not. But you look at the influence of resolution, but what about the influence of the different schemes that the atmospheric models have in their atmospheric boundary layer or for convection and so on? And is this more important or much less important than the resolution for all the results you show, like the maximum precipitation and so on?
Yeah, great question. I mean, this is somehow what I was alluding to when I was showing that plot of the precipitation as a function, precipitation variability as a function of resolution. You see there kind of that, there can be a huge, for a given resolution, there can be a huge spread and even quite a kind of almost bimodal, like, distribution almost in, which I assume is because of differences in things like the convective parameterization. So that, and those differences can often be like, as big as somehow the general shift in resolution that you see across the entire span, right? So in other words, the specifics of the convective parameterization do seem like they can really make a huge difference there. I guess my expectation though is that one's naive expectation though is that as the resolution continues to increase, then of course the parameterization, the specifics of the convective parameterization might become less important, and you might hope that then some golden future will turn off the convective parameterizations and they'll all kind of converge to where they ought to be. I don't have a good sense of when that might happen, but yeah, maybe that, I don't know if that, maybe that's a comment at least, if not an answer.
Thanks.
I mean, to some degree, the data, the simulations that will be produced now in the context of Destination Earth, that may become available, during the course of the year, and longer time series, perhaps into next year, that may be the first kilometer scale simulations without these convection schemes on altogether. And it may actually be of interest to revisit some of the questions related to the jet stream also with these type of models. It's a bit beyond scope of EERIE directly, but it may be interesting as well, to pick and look into this data, into these simulations as well.
Absolutely. And I think somehow, I mean, one of the perhaps nice things about thinking about it in this way is that things like, say daily precipitation variability, you might hope to constrain that quantity with even a relatively modest amount of data, right? So maybe we can kind of, if with only a couple of years of data, we're not going to be able to constrain blocking frequency, for example, but maybe we could constrain precipitation variability to some extent, and then kind of make an informed guess as to how good the blocking frequency or the jet variability will be in these models. So it might be a kind of potential way of overcoming the kind of sample size issues. Okay, I don't see any more hands, so unless anyone has any last comments, I guess we could finish at this point and start our Easter holidays. Oh, Ryan, go ahead.
Yes, just a remark. I like very much the way you referred to the paper of Battisti and Basugli. I think for me that was one of the crucial papers during my career, realizing how different AMIP and coupled runs are. One of the issues is that where SSDs and everything has a red spectrum, fluxes have a blue spectrum, and that really affects timescales, large timescales, and large spatial scales. So I'm, without knowing exactly the whole story behind it, I'm not that surprised that in a coupled simulation, ocean resolution really does has a large impact on those fluxes, because the atmosphere cannot adapt easily to the scale of the ocean and get, say, strong blue fluxes, but still have large variability. So I think it's nice that this old paper came up again, and
Yeah,
the idea to that, because it's really addresses a very fundamental point in air-sea coupling. What a very nice idea, I would say.
yeah, no, the credit for me learning about this paper was an anonymous review on a paper I published about a year ago, where I originally included some analysis where I was essentially looking at comparing an AMIP to a coupled situation and trying to infer something, and then the reviewer correctly pointed out that this is just completely wrong. The argument is completely wrong because of Basugli and Battisti. So I had to basically remove that entire bit of analysis from the paper. Yeah, now I'm very careful about that. So yeah, it's a very good paper.
Yeah.
Okay, well, we're at the hour now on the recording, so why don't we call it a day there. And yeah, thanks again for coming, and yeah.
Thank you very much, Kristian.
Thanks.
Thanks a lot.
Bye.
I like the presentation very much.
Thanks very much.
Thanks.
Yeah. Bye.